Welcome dear learners. We are studying quantum chemistry. In this module, we are studying about the term symbols. The contents of this module are microstates, term symbols, atomic term symbol determination, selection rules, spectral lines of hydrogen atom, Zeeman effect and the Stark effect. First of all, we are studying about microstate. Each different arrangement of electrons in a set of orbital has a slightly different energy and is called a microstate. Based on electronic arrangement, we can calculate number of microstates. Using this expression, number of microstate is equal to n factorial divided by r factorial into n minus r factorial. Here, n represents twice the number of orbitals and r represents number of electrons already present in the configuration. That is, number of microstate associated with a particular electronic arrangement can be calculated by using the expression n factorial divided by r factorial into n minus r factorial. Now, we can do some examples associated with the number of microstates for a P2 arrangement. We know number of microstate is calculated by the expression n factorial divided by r factorial into n minus r factorial. Here, n represents twice the number of orbitals or number of orbitals multiplied by 2. So, for a P2 arrangement, n is equal to, there are 3 p orbitals, px, py and pz. Therefore, n is equal to 2 into 3, twice the number of orbitals. So, n is equal to 6 and r is equal to 2 because it contains only 2 electrons. The P2 configuration contains only 2 electrons. Now, we can compute the microstate using the relation. Number of microstate is equal to 6 factorial divided by 2 factorial into 6 minus 2 factorial. That is equal to 6 factorial divided by 2 factorial into 4 factorial. The numerator I can simply represent as 6 into 5 into 4 factorial. So, 6 factorial, n factorial can be represented as n into n minus 1 factorial. So, 6 factorial can be represented as 6 into 5 into 4 factorial divided by 2 factorial into 4 factorial. 4 factorial vanishes. So, number of microstate is equal to 30 divided by 2 factorial. 2 factorial means 1 into 2 or 2 into 1. 2 into 1 is equal to 2. So, number of microstates possible for a P2 arrangement, for a P2 configuration, that is equal to 15. So, by using the expression n factorial divided by r factorial into n minus r factorial, it is possible to find out the number of microstate associated with every electronic configuration. That is about the microstate. Now, we can easily calculate the microstate for a D2 arrangement by proceeding in the exact way as we adopted in the P2 case. Here, the example is a D2 electronic arrangement, and for the D2 electronic arrangement, n is equal to 10, that is there are 5 d orbitals. n is equal to twice the number of orbital. So 2 into 5, that is equal to 10, and r is the number of electrons already present, that is equal to 2. Therefore, number of microstate is given by n factorial, that is 10 factorial divided by 2 factorial into 10 minus 2 factorial, that is equal to 10 factorial divided by 2 factorial into 8 factorial. 10 factorial can be represented as 10 into 9 into 8 factorial divided by 2 factorial is 1 into 2, that is equal to 2 into 8 factorial. 8 factorial, 8 factorial vanishes. So the result is 90 divided by 2, and that is equal to 45. So number of microstates associated with the D2 electronic arrangement equal to 45. So we proved that for a P2 configuration, number of microstate is equal to 15 or 15, and for a D2 electronic configuration, number of microstate is equal to 45. Now, this table illustrates number of microstates associated with the electronic configuration from P1 to P6. For a P1 configuration, number of microstate is equal to 6, and P2, this is already proved, P2 it is equal to 15. For a P3 arrangement, it is equal to 20. For a P4 arrangement, again 15. For a P5, it is equal to 6. P6, it is equal to 1. So this chart represents different microstates or number of microstates possible for the electronic arrangement from P1 to P6. Similarly, this chart illustrates number of possible microstates associated with D1 to D10 electronic configuration. So the electronic configuration, if it is D1, number of microstate will be 10, and for D2 it is equal to 45, this we have already proved, and for D3 configuration, number of microstate is equal to 120, for D4 it is equal to 210, for D5 it is equal to 252, then again diminishing is in the regular systematic order, 210, 210, 120, 120, 45, 45, 10, 10, in a symmetric way, there is an increase as well as a decrease. So number of microstate increases, reaches a maximum, then decreases. So from this chart it can be concluded that for maximum number of unpaired electrons, associated microstate will also be high. So simply we can say that number of microstate increases with increase in number of unpaired electrons. See the case for D5 configuration. It is an arrangement, D5 configuration in the ground state. You know there are 5 d orbitals, and the 5 d orbitals have unpaired electron in every orbital each. So this is the maximum number of unpaired electron possible, and this arrangement is a D5 arrangement, and for D5 arrangement the maximum number of microstate is also possible, and that is equal to 252. So we can simply conclude that number of microstate increases with increase in number of unpaired electrons. So if we are taking P arrangement, P3 is associated with the highest number of microstate. Similarly D5. If we are considering F arrangement or F orbitals, F7 is having highest number of microstates. Now we are moving on to the very important part of the discussion, that is term symbols. What are term symbols? In quantum mechanics, the term symbol is an abbreviated description of angular momentum quantum number in a multi-electron atom. Angular momentum quantum numbers in a multi-electron atom. Angular momentum has two components. For an electron, there are two components of angular momentum. They are the spin component and the orbital component. So the term symbol is an abbreviated notation, description of the spin as well as the orbital angular momentum quantum number in a multi-electron system. It is related with the energy level of a given electronic configuration. Hence, the term symbol can also be considered as a shorthand representation of energy associated with a particular electronic arrangement. This is about the definition of term symbol. Now, in computing the term symbol, the spin-orbit coupling interaction. Spin is denoted as S or spin angular momentum quantum number. Orbit angular momentum is represented by capital L. So, in computing the term symbol, we have to consider the spin-orbit coupling interaction or LS coupling interaction, or we have to assume the LS coupling. The spin-orbit coupling or LS coupling is otherwise called Russell-Sanders coupling. Moreover, the ground term. What do you mean by the case ground state? Ground state is the more stable arrangement where energy is minimum. The arrangement with the minimum energy is said to be the ground state, or highest stability is associated with the ground state. And we can determine the ground state term symbol by using a set of rules called Hund's rules. So, Hund's rule help us to calculate, to compute the ground state term symbol. Now, the atomic term symbol. The atomic term symbol is given by this representation. 2s plus 1 Lj. 2s plus 1 Lj. And this is the atomic term symbol. We can do the discussion on every parameter that appear in this equation. Here, capital S represents total spin quantum number, or we can simply say total spin angular momentum quantum number. And the parameter 2s plus 1 is known as the spin multiplicity. Now, capital L, it represents total orbital quantum number, or we can say L as total orbital angular momentum quantum number. Finally, there is a term called J. J is called total angular momentum quantum number. Total angular momentum is the vector sum of spin angular momentum and orbital angular momentum. So, absolutely no doubt J consists of L and S. So, there is LS coupling in finding out the value of J. Now, we can move on to details of each and every term that appeared in the expression for the term symbol. First of all, the total spin quantum number S. The total spin quantum number S or capital S is given by sigma ms, where ms represents the spin quantum number of unpaired electron present in the system. Suppose we are having a configuration that is nothing but P2 configuration. The P2 configuration can be represented like this. There are 3 p orbitals, and we can see as per the ground state electronic arrangement obeying the Hund's rule, the 2 electrons must have same spin. So, these 2 electrons have same spin, and these 2 electrons are now present in the clockwise spin. So, for the first electron ms equal to plus half, and for the second electron ms also plus half. So, the sum of ms, that is half plus half, that is equal to 1. But we have to make one thing. If these 2 electrons are in anti-clockwise direction, then this is the arrangement. Here the total spin is equal to minus half plus minus half, that is equal to minus 1. And we are taking only magnitude, not looking into the sign. After taking the summation, we have to take the modulus. So, total spin quantum number or total spin angular momentum quantum number is obtained by taking the summation of the spin quantum numbers of the unpaired electrons present in the system and finally taking the modulus. So, for this arrangement and this arrangement, we are getting the value of S is equal to 1. That about the spin quantum number. So, to find out the spin quantum number, we have to look on the electronic configuration and pick out the unpaired electrons and add their spin quantum numbers. Finally, take the magnitude. This will give the total spin quantum number capital S. Now, the second term, the spin multiplicity. This is a very, very important term. After determining the total spin quantum number S, we have to find out another parameter. That parameter is 2S plus 1. This 2S plus 1 is called the spin multiplicity. 2S plus 1 is called the spin multiplicity. Suppose we are having a system of two unpaired electrons. And these two unpaired electrons have the same spin. Then the value of S is equal to 1, which implies 2S plus 1 is equal to 2 into 1 plus 1, that is equal to 3. If 2S plus 1 is equal to 3, you can call that state as a triplet state. Now, suppose we are having a system of two unpaired electrons. One is having clockwise spin and other one is having anti-clockwise spin. Then we can say that S is equal to plus half plus minus half, so S is equal to 0, which implies that 2S plus 1 equal to 2 into 0 plus 1, that is equal to 1. If 2S plus 1 is equal to 1, you can call that state as singlet state. So, this is very, very important, singlet state. So, you are familiar with the singlet oxygen, triplet oxygen, etc. Oxygen molecule contains two unpaired electrons. If two unpaired electrons have the same spin multiplicity will be 3, and such an oxygen is said to be the triplet oxygen. If two unpaired electrons have opposite spin, then the value of S, total spin quantum number capital S, is equal to 0, which implies that 2S plus 1 is equal to 1. That state is called a singlet state. So, S is total spin quantum number and the parameter 2S plus 1 is called spin multiplicity. Now, we can move on to the very, very important quantum number or the most significant quantum number in the term symbol, that is total orbital quantum number. It is otherwise called the total orbital angular momentum quantum number, and the value of capital N can be computed like this: sigma ml modulus. What is meant by sigma ml? Sigma stands for summation. ML stands for magnetic quantum number. So, I will illustrate this by taking an example. Let us take a P2 configuration. And now I am representing the P2 arrangement. You know there are 3 p orbitals, px, py and pz. And I am representing the value of ml here. It is -1. This is 0. This is +1. And our 2 electrons are present in these two cases. Therefore, our unpaired electrons are present in ml equal to -1 orbital and ml is equal to 0. So, the L value of the present system is summation of this ml, that is -1 plus 0, that is equal to -1, and finally you have to take the modulus, so L is equal to 1. Remember the very important fact, the value of L is otherwise called term of the term symbol. Value of capital L is known as term of the term symbol. And we have to keep some important notations in mind also. If value of L is equal to 0, you can term, the term is S. It may be 1, it may be 2, it may be 3, it may be 4, etc., etc. So, the terms will also be different. If L is equal to 1, you are getting capital P term. If L is equal to 2, you are getting capital D term. If L is equal to 3, you are getting capital F term. Then this is G term and so on. So, therefore, the value of L, which is equal to modulus of sigma ml, will give the term of the term symbol. L is equal to 0 represents S term. L is equal to 1 represents the P term, L is equal to 2 represents the D term, 3 represents F term, and so on. This about total orbital quantum number or total orbital angular momentum quantum number or the term of the term symbol. Now, the last parameter that appear in the term symbol representation, that is total angular momentum quantum number denoted as J. The total angular momentum, as we know, is a vector sum of spin angular momentum and orbital angular momentum. Spin angular momentum is represented by the quantum number capital S. Orbital angular momentum is represented by the quantum number capital L. Therefore, the total angular momentum quantum number J can be represented as a vector sum of L and S. This means J can have values ranging from modulus of L plus S, L plus S minus 1, L plus S minus 2, moving on to final value modulus of L minus S. Thus, it is very, very important to keep this relation in your mind. The total angular momentum quantum number capital J is ranging from L plus S up to L minus S by a difference of 1 unit each. L plus S minus 1, L plus S minus 2, etc., etc. The last value is L minus S. And for the ground state configuration, we are selecting any one of the J value that is based on Hund's rule that we will discuss later. So, J value ranging from modulus of L plus S minus 1, L plus S minus 2, etc. And the last possible value is L minus S. That all about the total angular momentum quantum number capital J. So, we can find out J from the values of L as well as S. So, we will get the value of J. Now, ground state term symbol. I already mentioned that term symbol is a shorthand representation of angular momentum quantum numbers in a particular electronic arrangement. If the electronic arrangement changes, then the term symbol also changes. So, for a particular configuration, there are different possibilities of getting more than one term symbol in the grounded term symbol, excited term symbol, so on so. What we are focusing now is about ground state term symbol. Once the terms are known, we can arrange them in the increasing order of their energy. And the ground term is the term with the minimal energy. And the ground term can be determined by using a set of rules called the Hund's rule. What are the statements of the Hund's rule? This is the first statement. The terms are placed in the order depending on their multiplicity and hence their S value. The most stable state has highest multiplicity, or S value should be high. We know multiplicity is equal to 2S plus 1. In order to increase 2S plus 1, we have to increase S. So, for different terms, the term with the highest multiplicity is having minimum energy or more stable term. That means stability decreases as the value of S decreases. Stability proportional to value of S. Stability proportional to 2S plus 1. Stability proportional to multiplicity. So, for a set of terms, pick out those terms with the highest multiplicity that is associated with the minimum energy and the maximum stability. Moving on to the second statement of the Hund's rule. For a given values of S, the state with the highest L value is more stable. That means, if I will give you some terms, you have to pick out those terms with the highest multiplicity. If there are more than one terms with the similar multiplicity, then in that you pick term with the highest L value. So, the ground term or minimum energy term must have highest multiplicity. In that highest multiplicity, L value must be higher. If there is still ambiguity for a given value of S and L, smallest J value is more stable if the subshell is less than half-filled, and the biggest value is more stable if the subshell is more than half-filled. We know the fact that J can have two limiting values. The limiting values are modulus of L plus S, that is the highest value, and modulus of L minus S, that is the lowest value. Remember, if your configuration, electronic arrangement, is greater than half-filled, take the highest J value. If your configuration is less than half-filled, take the lowest J value. Suppose if the configuration is half-filled, then what will happen? L will be 0 and J is equal to S. J is equal to S. This is for half-filled arrangement. This is for less than half-filled arrangement. This is for greater than half-filled arrangement. These are about different possible values of J. So, by using the Hund's rule, we can determine the ground state term symbol associated with a particular electronic arrangement. Now, we can take some illustrative examples for ground state term symbol. First of all, determine the ground state term symbol for a P2 configuration. You know there are 3 p orbitals, and hence I am representing 3 p orbitals. I am going to mark the ML values, magnetic quantum number values at the top. It is equal to -1, it is equal to 0, it is also equal to +1. Now I am representing the P2 arrangement based on Hund's rule. You know about the Hund's rule. Pairing of electrons in degenerate orbital takes place only after all the available orbitals are singly occupied. And these singly occupied orbitals must have the same spin also. Based on that, I am representing the P2 configuration like this: one electron with the clockwise spin. The second electron is also with the clockwise spin. And first of all, I have to compute the value of S. And you know S is equal to modulus of sigma ms. By adopting the clockwise configuration or arrangement, ms equal to plus of, ms equal to plus of, so S is equal to half plus of, that is equal to 1. If you are knowing the value of S, then you can easily find out the value of the multiplicity 2s plus 1. Multiplicity 2s plus 1 is equal to 2 into 1 plus 1, that is equal to 3. So you got to 2 parameters, that is total spin quantum number and spin multiplicity. And now you know the term symbol 2s plus 1 Lj, out of which I got 2s plus 1, that is a multiplicity. Multiplicity is equal to 3. Then I have to determine 2 more parameters: total angular momentum quantum number J and total orbital angular momentum quantum number capital L. In order to determine capital L or term, we have to use the term sigma modulus of ML. Modulus of sigma ML. So ML values are here -1 plus 0. -1 plus 0 is equal to -1. If you are taking the modulus, it is equal to 1. You know the fact that L is equal to 0, 1, 2, 3. Corresponding terms are S term, P term, D term and F term. Since the value of L is equal to 1, the term is nothing but P term. So it implies the P term. L is equal to 1 and the corresponding term will be P term. And finally, we have to compute the value of J. You know the value of J is equal to L plus S up to L minus S. Since P2 arrangement, you know the maximum number of electrons that can be accommodated in a P subshell is equal to 6. So, the P2 arrangement is less than half-filled, so definitely no doubt. As per the Hund's rule, J value will be L minus S. Here also you can use modulus. So, what is the value of L? L is equal to 1. And what is the value of S? 1 minus 1. L is equal to 1, 1 minus 1, 1 minus 1 is equal to 0. So, value of J is equal to 0. So, now we have to put all the values in this expression. 2s plus 1, that is equal to 3. L value is equal to 1, that means a P term, and J value is equal to 0. So 3P0. 3P0 is the ground state term symbol for a P2 electronic configuration. Whether it may be 2P2, 3P2, 4P2, whatever may be, for P2 arrangement, the term symbol will be common, and that is equal to 3P0. 2s plus 1 is equal to 3, L is equal to 1, so P term, and J is equal to 0 since the electronic arrangement is less than half filled. So, by adopting the Hund's rule, we can determine the ground state of P2 arrangement as 3P0. Now we can move on to another illustrative example. That is, we are going to discuss the ground state term symbol for a D3 configuration. First of all, we have to represent the 5 d orbitals and their ML values. There are 5 d orbitals. ML values are -2, -1, 0, 1 and 2. This is about the values ML. And we have to represent the D3 arrangement based on Hund's rule. One electron is here, another one is here, another electron is also here. Therefore, S value is equal to modulus of sigma ms, that is equal to half plus half plus half, that is equal to 3 by 2. S is equal to 3 by 2. It may be clockwise or anti-clockwise. All may be in clockwise arrangement or all may be in anti-clockwise arrangement. If I am taking the modulus, then the value of S will be equal to 3 by 2. Which implies 2s plus 1 will be what? 2 into 3 by 2 plus 1. 2 vanishes, that is equal to 4. This about the multiplicity. Now we have to determine the value of L. L is equal to modulus of sigma ml. Sigma ml is equal to -2 plus -1 plus 0, that is equal to -3. Modulus of -3, that is equal to 3. L is equal to 0 S term, L is equal to 1 P term, L is equal to 2 D term, L is equal to 3, that is nothing but the F term. So L is equal to 3 and it implies F term. And we have to finally compute the value of J to get to the ground state term symbol. We are discussing about the D3 arrangement. The maximum number of electrons that can be placed in D subshell is 10. So half filled arrangement is D5. So D3 is less than half filled. So for the ground state, the J value must be minimum, that is modulus of L minus S. You know, L is equal to 3 and S is equal to 3 by 2. S is equal to 3 by 2. 3 minus 3 by 2, that is again 3 by 2. So the ground state term symbol for D3 arrangement is nothing but 2s plus 1 Lj equal to 2s plus 1 value, that is equal to 4, and L is equal to 3, that means F term 4 of, and that is 4 of J value is equal to 3 by 2, that is equal to 3 by 2. Hence 4 of 3 by 2 will be the ground state term symbol for a D3 configuration. Now this is another illustrative example where we are taking a metal ion. The metal ion is nickel 2 plus. And for nickel, we have to familiarize the ground state electronic configuration, outer configuration. 3d8 to 4s2 with atomic number 28 is the electronic arrangement of nickel. And here the question contains nickel 2 plus. So the arrangement is 4s vanishes and 3d8 will be the arrangement. 3d8 arrangement can be represented like this. There are 5 d orbitals. So arrangement is 1, 2, 3, 4, 5, 6, 7 and 8. -1, -2, -1, 0, +1, +2 will be the values of ML, and we have to compute S first. We can see the presence of 2 unpaired electrons, so S is equal to 1. So spin multiplicity 2s plus 1, that is equal to 3. 2s plus 1 is equal to 3. And we have to compute sigma ML modulus, that is equal to L. So in order to compute the L value, we have to do one thing for simplicity here. You need not consider the contribution from the completely filled orbital. So you can ignore these 3 orbitals because they are paired already. So we have to consider only ML values of those orbitals with unpaired electron. So this is +1, this is +2. So ML is equal to 1 plus 2, that is equal to 3. Again this implies the F term. Now finally we have to discuss about J. This is a D8 arrangement. D5 is the half-filled configuration. So D8 configuration is greater than half-filled and J value definitely L plus S according to Han's rule. The value of F is equal to 3 and S is equal to 1, therefore J is equal to 4. So we got all the values in this term symbol 2S plus 1 Lj, and we have to substitute the values also. Since S is equal to 1, 2S plus 1 is equal to 3 and L is equal to 3, the term is nothing but a F term, and J is greater than half-filled, J is equal to L plus S, so 3 plus 1 that is equal to 3F4. This is the ground state term symbol for a nickel 2 plus ion. That all about the determination of the ground state term symbol through examples. Next part, whole formulation or whole formalism. When a subshell is more than half full, it is simpler and more convenient to work out the terms by considering the holes. Holes means deficiency of electrons, that is the vacancy of electrons in various orbitals. By considering holes, it can be concluded that Dn and D10 minus n give rise to identical terms. Moreover, Pn and P6 raised to n has a similar configuration. We can also write F raised to n is equal to F14 minus n. These arrangements have a similar ground term symbol. Based on this, we can find out the whole formalism. We can apply whole formulation in configuration ranging from D1 to D10. This is the arrangement. For D1, the arrangement is equivalent with D9. D2 equivalent with D8. D3 equivalent with D7. D4 equivalent with D6. This and D5 is equivalent to D5 itself. This happened due to whole formulation. If you are excluding the value of J, D, F, F, D, 2D, 3F, 4F, 5D. This will be the ground term. This means that D1 and D9 has a term symbol 2D, D2 and D8 has a term symbol 3F, D3 and D7 has a term symbol 4F, D4 and D6 has a term symbol 5D. This is about the whole formulation in configuration Dn and D raised to 10 minus n. Now, selection rules for electronic transition between term symbols. The selection rules are restrictions that govern the possible or allowed transition from one state to another. In the case of atomic spectra, the selection rules are given here. Delta L is equal to plus or minus 1, delta S is equal to 0, and delta J is equal to 0 and plus or minus 1. Where L is the total angular momentum quantum number, S is the total spin quantum number, and J represents total angular momentum quantum number. The selection rules have been reduced experimentally and corroborated theoretically. And based on this, we can do this problem. Among these, which transitions are allowed? These are the set of selection rules. First of all, we can take this transition, 2S to 2D transition. 2S to 2D transition. Since multiplicity is same, absolutely no doubt, delta S is equal to 0, that is okay. J value is not given, so last selection rule is not adopted here. So we have to check the transition from S to D. We know that L is equal to 0, 1, 2, 3, 4. L is equal to 0, S term, P term, D term, F term, G term, like that. So the transition is from S to D, S to D. So delta L is equal to 2 minus 0, 2 minus 0, delta L is equal to 2 minus 0, that is equal to 2. So no doubt this transition is not allowed because allowed delta value is only plus or minus 1. If one rule is not valid, the entire transition will be not possible. Coming to the second transition, 2P to S. Here also S is not a trouble, not a factor. And we have to look on the transition from P to S. P and S are two adjacent terms, so absolutely no doubt delta L will be 0 minus 1, that for this transition delta L value is equal to minus 1, that is allowed. So this transition is allowed. And we are moving to next transition, that is the 2f to 2p transition. Here also 2 J value is not mentioned here. S value is okay because delta S is equal to 0. Since multiplicity is same, S is same in both of the situations. So delta S is 0, it is implied. And we have to look on the transition from F to P. F and P are not any adjacent terms. So 3 minus 1, delta L is equal to 2. So this transition is also forbidden. And we are finally looking on the last transition 2 to 2, S to S. Delta L is equal to 0 here. S to S is delta L is equal to 0. Delta L is equal to 0 is also forbidden. So the last transition is forbidden. So among these four, as per the selection rule, the one and only allowed transition is from 2p to 2s transition. Now, spectral lines of hydrogen atom. Atomic term symbols are sometimes called spectroscopic term symbols because atomic spectral lines can be assigned to transition between states that are described by atomic term symbols. The spectrum of hydrogen is the simplest of all spectra. This spectrum is governed by selection rules also. The spectrum governed by the selection rule for transition between orbitals. This is the selection rule for transition in the hydrogen spectrum. Delta N is anything. N represents the principal quantum number. Delta L is equal to plus or minus 1. L is the azimuthal quantum number. We can see that electron in the ground state. Electron is already present in the ground state in the 1s orbital of hydrogen. It can undergo transition to any p state. 1s, NB, N greater than or equal to 2. The 2p electron can undergo transition to either an S state or D state. That is, 2p electron can move on to NS or ND state based on these set of selection rules. And if we look closely, the Lyman series of atomic hydrogen, we see the allowed transitions into the ground state. For transition between terms, there are two p terms possible. The p term symbols are 2p1 by 2 and 2p3 by 2. The allowed transitions are 2p1 by 2 to 1s transition and 2p3 by 2 to 1s transition governed by this set of selection rules. Now, fine structure. The increased spectral complexity caused by spin orbit coupling interaction is called the fine structure. That is, the fine structure occurs due to coupling of orbital and spin angular momentum of electron or LS coupling. Thus, 1s 2p transition in hydrogen atom will give rise to a doublet due to spin orbit coupling. The spin orbit coupling is shown here. If there is no spin orbit coupling, there is only one line. As a result of the spin orbit coupling interaction, the p term split into 2. Therefore, this one signal split into 2, that is a doublet. And we are now discussing the Seaman effect. We already learned about the Seaman effect. The splitting up of the spectral lines in the presence of the applied magnetic field is called the Seaman effect. The applied magnetic field B splits the term with the given J value into 2J plus 1 sublevels characterized by the quantum number Mj, corresponding to which Mj represents the component of J along the Z direction. The selection rule for Seaman transition or Seaman effect is delta Mj equal to 0 plus or minus 1. Based on this, we can illustrate the Seaman effect with the help of this diagram. Here there is no magnetic field, so only one line is here. As a result of the external magnetic field, this line is split into 3. So there are 3 possible transitions based on the above selection rule, delta Mj equal to 0 plus or minus 1. So, in the presence of the magnetic field, this one signal splitted into 3 signals. This is called the Seaman effect, and this picture is called the Seaman pattern. Moving on to the final part of the discussion, that is Stark effect. Stark effect is absolutely the splitting of the spectral line under the influence of an external electric field. Let the electric field is E. Then the electric field causes the splitting of the spectral lines into further, which is discovered by German physicist J. Stark, hence the name Stark effect. And the Stark effect occurs due to the interaction of electric field and induced electric dipole moment as a result of electron polarization. The energy of interaction in a Stark effect is given by E internal is equal to minus mu into E. Thus, we have discussed all aspects about the term symbols, ground state term symbols, Seaman effect and Stark effect. That all about this module. Have a nice learning experience. Thank you. bye.